In this video, we're going to talk about factoring polynomial expressions. And just so there's no confusion, recall that in mathematics, we say that an expression is a monomial if it consists of a single power of x, possibly multiplied by a constant. So x squared is an example of a monomial. Likewise, a binomial consists of two such terms that are added together. A trinomial would consist of three such terms that are added together. And in general, any of these expressions and others where we take some arbitrary number of terms and add them together is called a polynomial, the prefix poly meaning many. To understand what factoring polynomial expressions is all about, let's look at a simple example that involves multiplying two polynomial expressions. In this case, the monomial x, highlighted in blue, and the binomial x squared plus 3 in white. The distributive property shows us how addition and multiplication interact with one another in such a situation, and tells us that this product can be obtained by multiplying the x by each term in the binomial. So it's going to be x times x squared plus x times 3. And this, of course, simplifies to x cubed plus 3x. In moving from the first step to the third step of this calculation, we distributed x across x squared plus 3. But what if we wanted to move in exactly the other direction, from the third step in the calculation to the first? What if we wanted to express x cubed plus 3x as a product of two other polynomials? Well, that's nothing other than an example of factoring a polynomial. Let's have a look at a more interesting example. Suppose we want to multiply the two binomials x plus a times x plus b by one another. Well, then this time, using FOIL and what we know about multiplication, we would obtain x times x plus a times x plus b times x, and finally plus a b, which simplifies to x squared plus a plus b times x plus a b. By the way, if it's not clear to you why FOIL actually works, have a look at this picture, which shows a rectangle that measures x plus a on one side and x plus b on another. What the picture clearly shows is that the area of the rectangle, namely x plus a times x plus b, consists of four parts: the area of the white square, which is x squared, the area of the blue rectangle, which is ax, the area of the yellow rectangle, which is bx, and the area of the red rectangle, which is ab. This accounts for the four terms that appear in the expansion of x plus a times x plus b. Now, back to our example. We know how to multiply or distribute x plus a across x plus b, but how can we move in the other direction? How can we go from the polynomial that appears in our third step and factor it to obtain the two polynomials that appear in the first step? Well, taking a careful look at the coefficients that appear in our third step gives away the answer. Notice how the constant term, ab, and the coefficient of x are related to each other in a certain way. Indeed, what we have here are two numbers, a and b, whose product is exactly the constant term and whose sum is the coefficient of x. And this actually leads us to a general principle. The general principle is that to factor a polynomial of the form x squared plus ax plus b, what we need to do is find two numbers whose product is equal to b and whose sum is equal to a. For example, to factor the polynomial x squared plus x minus 6, thus enabling us to write it in the form x plus some constant times x plus some other constant, what we need to do is look for two numbers whose product is equal to -6 and whose sum is equal to the coefficient of x, which here is just 1. And you don't have to think too much before realizing that the answer here is 3 and -2, which we can simply write in our two factors now. And indeed, notice that 3 times -2 is -6, and that 3 plus -2 is 1. Now, fair warning, factoring can, in many cases, be extremely difficult, especially if the polynomials in question are very large, and sometimes it's even impossible. However, quadratic expressions can very often be factored. Let's take a look at one more example that's a bit more tricky than the previous one. So here we'd like to factor once again. And the key difficulty that's introduced with this example is that the coefficient of the x squared term is no longer equal to 1. This time the coefficient happens to equal 2. So let's think about how to proceed here. We'll again want two factors, which I will sort of write in here using just empty parentheses for the time being. But notice that we can't simply have two factors of the form x plus some constant. The problem is that when multiplying these two x terms, we would end up with only x squared, not 2x squared, which is what we want. So the thing to do is to make sure that the coefficients of our two x terms in each factor multiply together to yield 2. And here, the most natural way to make that happen is to select one of the coefficients to be 2 and the other one to be 1. Once that's taken care of, we can actually proceed as before, using our general principle. Let's break it down. We're going to want to add two constants, which for the time being I'll just call a and b in our two factors. And they'll have to satisfy a couple properties. It will have to be the case that a times b, let me write that down, equals -5, right? That's the constant term in the left-hand side. And it will have to be the case that the coefficient of x in our expansion, which is a plus 2b, be equal to 9, which is the coefficient of x in the left-hand side. Just in case it's not clear, note that the a plus 2b term comes once again just by considering the product a times x and the product b times 2x. Finally, we just need to play around a bit and see what works. Since we know that a times b equals -5, it's natural to guess that a equals -1 and b equals 5. And sure enough, if that's the case, then we see that -1 plus 2 times 5, that's 10, is indeed equal to 9. And this shows us how to factor the original polynomial. We can write it in now. Our two factors take the form 2x minus 1 and x plus 5. Of course, it's also natural to have guessed that a equals 1 and b equals -5. But in that case, it would not be true that a plus 2b equals 9. So you would simply go back and make another guess and see if everything holds together.